19. Right, so 3 more. All right, so I guess the other 3 will just catch up to us. I think they're still doing something, or they have their own things that they still need to do. Anyway, so we will start now our discussion on Module 1, Part 3. So again, before we start, do you guys have a question or a clarification?
None po.
All right. So again, feel free to ask me anytime if ever that you have a question. All right, so start with, we have here the quantifiers. So last meeting, we have discussed the laws of logic, connectives, the symbols, and so on and so forth. Okay, but that one is still lacking to have a complete proposition. Okay, so logic using propositions are incapable of describing most or maybe some of the statements in mathematics and computer science, such as the use of variables. So that is why we have quantifiers to add variables. So we can have one variable, two variables, or three variables in a statement or a proposition. So again, as we all know, a propositional function, or p of x, is not a proposition until it has a truth value. Okay, so if we don't know the value of that proposition or of that variable, then that one is just a propositional function. Okay, it will never become a legitimate proposition or a legitimate statement. So up to this point, we could only do this by assigning a value to such variable or to our variable. So for example, take a look on this one. So if p of x represent x is greater than 0, this will never be ever a proposition unless we have uh, a true value for this x. Okay, so never, uh, even though this one is true or false, so this one will become a proposition if this one now has a final value. So for example, find the truth value for p of 4. So assuming that the value for x or this proposition is 4. So if we replace this x by 4, then we could say that this statement now is true. Okay. And since we can now say that this one is true or false, then this one now is a proposition. Okay. So we have two types, or two ways rather, in turning a propositional function into a proposition. So we have here universal and then existential. Okay. So this is the symbol for universal, an inverted A. And then this is the symbol for existential, which is a flip letter E. Okay. So let's start with universal. So from the word itself, universal, it's talking about everything, okay, or all. Okay. So this one is universally quantified statement. So we have here the universal x, which is p of x, wherein universal x, or this inverted a, is the universal quantifier, and then this p of x is just the proposition. Okay, which means that this universal, for every x, p of x is true, or for any x, p of x is also true, or for all x, p of x is true. So that's or those are the ways on how to read this universal quantifier. Okay, so as you can see, in every value of x, p of x should be true, or any value of x, p of x should be true, or basically all of the values that is possible that we can substitute or replace this x, so it should be true to make this proposition true. Okay, so hearing the word universal, so you might already have an idea for that one. So you can read universal in three ways. Okay, so we have this scenario wherein universal x p of x is true if p of x is true for every x in its domain. Okay, so if there is at least one x that is not true, okay, then that one is already a false statement or a false proposition. Okay, so that is why in here the opposite here is if there is at least one false for at least one x in its domain, then that is already false. Okay, so in universal, all of the possible variables or values for x should be true to make it true, okay, all throughout. Because if no, then that is not uh, a legitimate true universal. Okay, so moving on, we have here existential quantifiers. So this is, you can say that this is the opposite of the universal, wherein it symbolizes by this one, wherein it's again flip the letter E, wherein this letter E is the existential quantifier, and then E of X is just again the proposition. So you can read this one as for some X, or for at least one X, or there exists X. So all of those three are saying that there should be at least one, or there should be some, or there should be one false or one true on that statement to be called an existential. Okay, so just take a look on this scenario. So existential x, p of x is true if p of x is true for at least one x in its domain. So we only need one. Okay, but take note, the other should be false, or the other should be true. So it should be a mix of true and false. Okay, because if every x is already true, then that is not already an existential. That is already universal. Okay, so in here, for us to be able to say that this one is a true existential, there must be one true and then one false. Okay, so that is the minimum requirements for us to be able to say that it is an existential statement. And then the other one is if, of course, uh, existential x, p of x is false, if p of x is false for every x in its domain. Okay. So if there is no true values in every x that you're going to substitute, then that is not also an existential quantifier. Okay. Again, the minimum requirement is to have one true x and then one false x. All right. So did you guys get the idea of the universal and then existential quantifier?
Yes, sir.
Yes, sir.
Or
Yes, sir.
that's good
Yes,
then.
sir.
So just let me know if you guys are confused between those two, okay, so that I can explain it more to you. All right, so if no one is confused, then let's proceed to the next one. Okay, so we have examples here for quantification. So validate the following quantified states. So number one, for every real number x, x squared is greater than or equal to 0. So in here, it's saying that this one is universally true, okay, in this kind of expression. So is this true or false for every real number of x? So just to remind you guys what is a real number, so actually it's any number, okay, that you can think of. So it could be rational, integers, whole numbers, or even irrational numbers. That is under real numbers. Okay, so is this true or false?
Mm.
Why? What is that number
Mm,
that will make it false? Anyone? So if you can find an example, at least one value, we call that one counter example. Okay. So if you can at least find one counter example, this one is already false. But if you cannot find any counter example, then this one is true. Simple as that. So what do you guys think? Is this true or false?
true.
True. So who's saying
Yes,
here
sir.
that
True.
number one is true? Do we have an answer of false? Anyone? All right. So I guess none. So are you guys saying that number one is true?
Yes, sir.
Okay, so number one is universally true, and then existentially false. Okay, or basically you can just say, this one is true. Okay. I'm just stating that one if it's universally or existentially. Okay. How about number two? For every real number x, If x is greater than 1, then x plus 1 is greater than 1. True or
True.
false?
True, sir.
False.
So number 2 is
False.
True.
why false?
Ay, true pala, sir. True pala. Sorry.
Take note, yes, we have the
Mm.
condition every real number x wherein it's under negative and positive values. But we also have this second condition wherein it is saying that x should be only greater than 1, so 2 and above. So you are going to start here with 2. So 2 plus 1 is 3, so it's already greater than 1. And above,
Okay, sir.
and then we'll just make this one super true. Okay, so number 2 is true. How about number 3? For every real number x, x squared minus 1 is greater than or equal to 0.
False.
False, sir.
False, sir.
Why? What is that number that will make this one false?
Zero. Ay,
Yeah, you're right.
zero.
0 is also a real number. So if you're going to replace this x by 0, then 0 squared is 0 minus 1 is negative 1. Wherein negative 1 is not greater than or equal to 0. So that's making number 3 a false statement. Okay? So in here, this one is existentially true, okay, but universally false. Right? So I hope you're getting already the idea of the usage of universal and then existential. Anyway, so yeah, that's how easy to identify a statement using for uh, kind of this reading wherein for every real number, for all, or for some, okay, or for at least one, and so on and so forth. Okay, so depending on the structure of the statement. Anyway, once you're done in understanding this one, then you can now proceed and answer our state work. Okay, so this one is only answerable by true or false. So supposedly, okay, if we are in a face-to-face format, I would ask you guys to have a counter example if ever that this one is false. Okay, but since we are in online distance learning, so I will only require you guys to answer this one using true or false. Okay, so you don't need to defend your answer if your answer is false. Okay, so just like what we did on the first three examples, just answer this one using a true or a false answer. Okay, so are we clear so far? I hope you guys have already actually answered this one since I have uploaded the module 1 part 3 ahead of time. So you guys have already an idea that you're going to do this one on your module. I mean on your canvas. Okay. So do you guys have any concerns regarding with this work, or is this clear? So no question.
No question, sir.
All right. So just answer this one on your canvas later on. Okay. Next one is having multiple quantifiers. Okay. So you can actually have multiple quantifiers on a statement. Like for example, you can have a universal value of x or some values of y or existential y for the proposition x and y. Okay. So you can read this one as for all x, there exists a y such that p of x and then y. Okay. Or you can have the other way around, which is having a existential x and then a universal y. So you can read this one as there exists an x that for all y. Okay. So I know that this kind of way of reading this statement is maybe different on how you construct your statement or sentence. So it's okay as long as you could say that you have a universal x and then existential y and then existential x and then universal y. Okay, so we are not in English subject, so I'm not that strict when it comes to constructing your own way of reading such expressions. Okay. Anyway, so that's it for multiple quantifiers. Next, we have here negation and then quantification. So just take note on this one. Okay, when we say negation of uh, quantifiers, the parenthesis is not or doesn't actually matter. Okay, so if you negate a quantifier, you're going to negate all of the values inside of that quantifier. So what do I mean by that? So later I'll give you guys an example on what I am talking about if you're going to negate everything. Okay. So this one means, if you're going to read this one, means there does not exist even one x in the universal set that makes p of x true. Okay. So you can disregard this one, but if you want to analyze this one, uh, then please do so. But you can disregard this one, okay? Because this is just a way on how to read such expressions. So if you're going to negate this one, so this existential will become universal, and then this positive p of x will become a negated p of x. Okay, so supposedly, if it's with the use of distributed properties, okay, so we will only distribute this one on the outer parenthesis. So it will not affect your inner parenthesis anymore if we are solving this one in a manner of, you know, common math, or just like what we have learned in algebra. So in here, parenthesis doesn't matter. Okay, so basically you're going to negate everything. Okay, no, nevertheless, of the counts of your parentheses. Okay, so that is why you have to negate this one, and then you have to negate this one also. So that's how we've come up with this equivalence logic. Okay, so if you negate this existential, it will become universal, and then if you negate this positive, of course, it will become negative. Okay, the same with this one. Okay, so means p of x is not true for all x in the universal set. So again, if you're going to distribute this one, this universal will become existential, and then this p of x will become negated p of x. So can you guys follow so far?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
So again, you can disregard this one, okay, because those are just ways on how to read such expressions. So this will just make you confused, matters if you're going to analyze this one. So just focus on this one. So if you negate existential, it will become universal. If you negate universal, it will become existential. Right, so let's have examples. So we have this expression, and then as you can see, here's a step-by-step process on how we've come up with this final result. So the first step, so we've distributed this one into the first parenthesis, which is this one. So again, this universal will become existential. Then again, so that you can follow easily. So the highlighted yellow is the changes from the past solution. So from here, we've changed this one. So this is our first step in negating such expressions. Next is, again, of course, distributing this one onto the next statement, wherein making this existential into universal, right? And then the last one is distributing this one onto your p of x and y, making this positive into negated p of x, y. Okay. So now we could say that this one is equally or logical equivalence with this one. Okay. We've just simply negated everything. Were you guys able to follow and how we come up with this result?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so very good. So this one is super easy anyway. So number two. Okay. So in number one, I've showed the step-by-step solution on how we come up with this result. So number two, I will not show the step-by-step solution anymore. So all you need to do is basically negate everything. Okay. So this existential will become universal, and then this universal will become existential, and then this positive will become negated p of x. Okay. So did you guys get number two?
Yes,
Yes,
sir.
sir.
Right.
Yes,
Yes,
sir.
sir.
Very good. Very good. Okay. So let's have an exercise. Okay. So we have this proposition. Okay. So this proposition now is a readable statement wherein we have universal x is an element of proposition n, wherein this n is actually have this readable proposition x value, wherein x is prime, or if x is prime, then x squared plus 1 is even. Okay. So again, we have here negation. So basically, we're just going to negate everything. Okay. So here's the first step. So distribute this one on the first statement or the first parenthesis. So this universal will become existential, and then what else? And then we're going to negate the proposition, okay, or the readable proposition letter X. So as you can see right here, if we're going to distribute this negation into the first statement, yes, it's doable. Like for example, this one will become X is not prime, but we cannot find, or there is actually no negated value of conditional. So that is why we're going to apply the laws of logic, wherein this P conditional Q is actually equivalent to negated P or Q. Okay? So you have to convert this conditional first into or into N. Okay, because that N can become or that or can become N. Okay, do you guys what I'm trying to say? So you cannot negate this one directly. Okay, so you have to find an equivalence in the laws of logic wherein this one is equal to or this one is equal to n. So any of those two, right? So in here we've just found out that this p conditional q is actually equal to negated p or q. Okay, so if I'm not mistaken, this one is number 18 in laws of logic, 18 or 21. I'm not pretty sure. Anyway, so you can find this one in the laws of logic. Okay, so from here we can now convert this one into this kind of expression. So yeah, so our negated value or negated sign is still in here, and then we're just going to follow this one. So this one is the letter P. So in here it's now negative, so we should follow this one for now. So X is not prime. So from positive to negative, wherein we just added not. And then this or, so from condition to or, so just put here or, and then just copy the last one as it is, which is x squared plus 1 is even. Okay. And then from there, you can now start distributing this negated symbol. So from negated P or Q, so this one is equal to not P and not Q. All right. So again, from x is not prime, okay, just negate that one again, and then you're going to go back on the original statement wherein x is prime. Okay. And then this or will become n, which is now this one. And then the last one will be negated. So from this to this. So as you can see, we found that even, so the opposite of even is actually odd. So we cannot just say that x squared plus 1 is not even, okay? Because we can answer here, let's say, you're actually trying to make the possibilities into a larger domain. Because in here, we're just saying that this one is even. So what is the complete opposite of even? That is odd, okay? So do not just say here is not even, because if it's not even, then we can also answer uh, integers or fraction or even pi number, okay, or any values, okay. So for us to to have a perfect match, what is the opposite on what is the opposite of even? So we should find any possible, okay, equivalence or opposite rather of that word. So in this scenario, the complete opposite of even is odd. Okay. So that is why this one now is equal to this one. So x is prime and x squared plus 1 is odd. Okay. So did you guys get it so far?
Yes, sir.
How about the others?
Yes, sir.
Yes, sir.
Uh,
Medyo, okay. So again, I think the only tricky part is this one, okay? Because maybe some of you or most of you will say here, let's say the negated value of this one is x squared plus 1 is not even. Okay, so do not do that one. If you can find a straight opposite of that word, then please do so, just like this one. The opposite of even is odd. Right, so let's have another example wherein we have this expression, and then we have to negate everything. So again, this existential will become universal, and then the SQ proposition will be negated. Okay, so we now have here the negated symbol, and then if you're going to distribute this one, so it is possible, since we can negate this greater than, we can also negate this and then we can also negate this equal. So from here, so what is the complete opposite of greater than? So you can say that it's less than or equal to. Okay. So if ever that you have answered here less than, I will also accept that one. Okay. So you can answer here less than or equal or just simply less than. Okay, so no problem. Okay, so that is the opposite of this greater than. And then the opposite of and is of course or. And then the opposite of equal is of course not equal. Okay. So simple as it is. We now have the negated result of this number 2. Did you guys understand this one so far?
Yes, sir.
Yes, sir.
All right, very good. So again, if you have a question or clarification, so feel free to ask me anytime. Anyway, so once you're done in trying to understand what is the negation of this expression, blah blah blah, so you can now answer these secrets. So I only gave 5 numbers. Okay. So yeah, I'll leave this one into you guys, and then I guess it's possible. All right, so answer this one using Microsoft Word, because we can also find the symbol in Microsoft. We can also find the symbol in Microsoft. So I guess no problem. So for equal, you can also find the not equal, and then for plus. Right, so take note, you don't need to change the x plus 3, x minus 3, x plus 3, and so on and so forth. So all you need to change is the equal, and then the other connectives, which is the and then the or, and then the greater than or less than. Okay, so those only. Okay, so no need to change the plus and minus. And then where can you find the other symbols? So just go to insert. So it's just the same in Microsoft Word. So go to insert and then click this equation, and then you will see those symbols. So we have here the not equal, less than, greater than, less than or equal, greater than or equal, the invert, the flip E, which is for existential, and then where is the universal? Universal. Can you guys see where is the inverted A?
Upper right, sir.
Upright, sir.
This one. Yeah. Okay, so this is for the universal. All right, so this one is doable in Microsoft. All right, so any questions so far regarding with your seat work?
None, sir.
None, sir.
All right, that is good then.
None.
Next, we have here proofs. So this one is actually an argument that establishes the truth of a theorem, which we have already did many times, like for example, using a truth table, okay, or using an equivalence rules, or even using inferencing rules or deductive. Okay, so in proofs, of course, there is always a hypothesis into a conclusion. Okay, so that is why we call that one proofs. Okay, so what is this equivalence rules? So this one is describing that logically equivalence is equal to this logical equivalence rule. You're saying that this one is equal to this expression. And then what is this inference rules or deductive? So this one is described when a weaker statement can be deduced from a stronger statement. So in inferencing rule, this one actually can be done, like for example, by having 5 variables or 5 hypotheses, and then concluding that this one can be concluded by using 1 variable or 2 variables only. So from 5 hypotheses into 2 conclusion or 1 conclusion. Okay, so I'll give you guys some examples on how to do inferencing. But for now, So take a look on these equivalence rules, wherein we're saying that this one or this expression is equal to this expression. So as you can see, we have here negation, implication, De Morgan's laws, commutative, associative, and so on and so forth. Okay, so those are equivalents. So we have already discussed those things, okay, in the laws of logic. So this is just actually just a recall, okay, wherein we can apply equivalence into inferencing. Okay, so I will not discuss this one anymore. Just try to recall this one on our uh, last discussion. Okay, so here's now the rules of inference. So to prove the theorem means to show that the implication is a tautology. Okay, so this is one thing that you have to take note. This is very, very important. In rules of inferencing, all of your hypothesis is concluded or assumed to be true. Okay, so for example, if this one negated p, if we have that kind of symbol negated p, the value of that one is still true. All right, unless there is another hypothesis wherein it is saying that that uh, true value or the true variable is actually false. So the only thing that can make that hypothesis to be false is another hypothesis or with the statement of another hypothesis. So if there is no another hypothesis that is saying that this one is false, then we assume that negated p is actually true. Okay. So yeah, I know this one is quite confusing when it comes to rules of inferencing versus the laws of logic or the using or with the use of truth table, because that negated is like nothing. Okay, so you still read that one as a true value, or that one is still a true value. Okay, that's why we call this one a tautology, because in every result, in all of the hypotheses, in all of the conclusion, the entire statement will become a tautology. Okay, so like for example, this expression is a tautology. Okay, so we have here the P conditional Q and then P and A, okay, which came from this expression. So this is the proof wherein if you're going to combine all of those with all of the possible combinations, so true, 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 false, false, true, false, false, all the results that you're going to get are true, okay, or just simply a tautology, right? So as you can see, we have here this expression, and then if you're going to read, to write this one into inference format, so it would become like this. So how did we write this one, or from this one into this one? So if you can see a symbol n, that one is like a separation into another hypothesis. So that is why we have this letter P to here, and then N is a separation, which is now another hypothesis, which is P conditional Q. And then the last one is conditional, wherein we could say that this hypothesis is equal to Q or concluded as Q. All right, so that's how you read this one into, or that's how you convert this one into this one. Anyway, we will continue this one later on, since I guess we now only have 10 seconds. So goodbye for now, and then just wait for the part 2. All right. So bye-bye. See you on part 2. So again, do you guys have a question or clarification?
None po.
None, sir.
All right then. Okay, so if you guys do not have a question, so let's now proceed to the next one. All right. So here's the inference form, wherein the above mentioned P1, P2, or up to P10 or P100, those are our hypothesis or premises. And then once you can see this horizontal line, which is separated from the hypothesis or premises, this is now our conclusion. So mostly, this conclusion is only one variable or two variables. Okay, but mostly one variable only. Okay, so again, the separator here, so this is your first hypothesis. The separator here is the and or the conjunction symbol. So we read this one as P1 and P2 and so on and so forth. Okay. Conditional. So this conditional here is actually equal to this horizontal line or equal. Okay. So P1, P2 up to Pn is equal to letter. All right. So that's how you read this inference form. Okay. So here are the basic rules of inference. So again, in hypothesis, we're always assuming that the value, okay, the initial value of your hypothesis is always true. So if P is true, then P will always be true. Okay. So in hypothesis, we assume that this one is true, then we can conclude now that this letter P is really true. Okay. So this will only be affected, or this will only become false if there is other, okay, if there is other uh, hypothesis that will make this one false. But since there is no other hypothesis aside from this one, then we could assume that this one is the conclusion. So here are the other examples. So the same with this one. So Q is always true. So we could conclude that this one is true. And then this negated R is always true. So we could conclude now that this one is always true. So basically, you can just simply copy this one, okay, regardless of the symbol or the negated, or if there is a negated or there is no negated symbol. Okay, so the assumption or the value of this one is always true. Okay, same with this one. Okay, just have a negated symbol. All right, so those are the laws or rules for identity. Okay, so next we have here conjunction and conjunctive simplification. So first is conjunction. So again, we read this one as P and Q. Okay, so in here, there are no other hypotheses which will make this one false and then this one also false. So we assume, okay, that they are true. So we could say that P and Q is true. Simple as that. Okay. So here are the other forms or other format. So we have here P and Q, okay, wherein there are no other hypothesis that is saying that P is false or Q is false. Then we could just simply say that P is true. So as you can see right here, we have two possible results. So if you have this kind of expression, and then assuming that their values is true, then you can answer P or Q. Okay. So either of those two actually. So they are both correct. Okay. Since their values are true. Okay. So it will not change our result as being or becoming true. So were you guys able to follow up to this point?
Yes, sir.
Yes, sir.
Yes, sir.
Sir.
So maybe at first this one is quite shocking or confusing because maybe this is your first time learning about rules of inference. So we'll be having, don't worry, we'll be having examples on this one on how to come up with such conclusion. Okay. So next we have here disjunction. Okay. So as you can see right here, this one is P. Okay. And then we could say that this P is concluded as P or Q. So this will not change the result, nevertheless, of the value of Q, because in OR, if there is one true, then the entire result is already true. So this is just a way to see that, you know, regardless of the value of our Q, the result is still true. So that is why they've shown here that the conclusion is P or Q, okay, instead of saying P only. Right? Or vice versa, we could say that if this one is Q, then we could say Q or P. Okay, because we have already assumed that this letter P is always true. Okay, so here are the other examples for disjunctive syllogism. So we have here P or Q. So again, the value for P or Q is already true. So P is true, Q is true. And then there is another hypothesis that came out wherein it is saying that our P from our first hypothesis is actually false, right? So again, in rules of inferencing, our result should be always true. Okay, so in here we should put here Q because we have already know that P is actually false. So we should conclude that the result must be Q because this one is already true. Okay, so the same with this one. In here, knowing that P or Q is always true, but then there is another hypothesis came up wherein it is saying that this hypothesis or this letter P is actually, this letter Q is actually false. Okay, so since we already know that this letter Q is false, then we have to answer P. Since in inference, we have to make a tautology result. Okay. So that is why we have an answer or conclusion here P, and then we have a conclusion here Q. All right. So were you guys able to follow at least 50%?
Yes, sir.
Yes, sir.
Yes,
So
sir.
here's the tip and trick. So your conclusion must always, okay, must always make the entire expression true. Okay. So that is your key points on how to identify what would be the conclusion. Okay. So that's how we've come up with Q or P. All right, so we have another two rules of inferencing here. We have the modus ponens and then the modus tollens. So modus ponens is actually a Latin word for meaning affirmative mode. And then for modus tollens, meaning denial mode. Okay, so modus ponens first. So in here, initially our value of P is already true. Okay, and then we have another hypothesis here wherein P conditional Q. Okay, so in here, okay, there's actually no tricky part in here since by default letter P is true, Q is also true. So if we can say this kind of statement, then the result is always the conclusion. Okay. So again, we have two hypotheses, which is just the same variable. And then whatever's the result, then that would be our final answer, which is true. Okay. And then we have another format here for modus ponens. We have here negated P, conditional Q. So again, assuming that negated P is true, conditional Q is also true. Okay. And then it is saying that negated P is really true. Okay. So do not be confused with this negated. So we're just saying that this negated P is actually really true. Okay, just by showing another negated P. So from here, we could see that those hypotheses is equal with the conclusion since we have assumed that they are uh, actually true. Okay, so quite tricky when it comes to having negated symbol. But then again, in hypothesis, we always assume that they are true. So, for example, this one is true already, but we have here another. Okay, this is a good example. I'll give you guys a scenario. So, so from here, this is the result, right? But then again, if you have oops, there you go. How to make this one thicker. All right. So if we have this kind of format or expression, so assuming that negated P conditional Q is true, so this one is true, and then the other one is true. But then again, there's another hypothesis came out wherein it is saying that this negated P is actually false. Okay, because we have a different result in here, wherein letter P is actually false. So false, conditional Q. Okay, so since our hypothesis is already false, then we have to copy the last one, which is true, since we want to have a result of true. Okay, so yeah, anyway, vice versa, either this one is actually true or false as long as the conclusion is true. If you can recall the truth table of conditional, nevertheless of the value of the hypothesis, as long as you have a true conclusion, the result will always be true. Okay, so that is why if we have this kind of setup, the answer is still Q. So were you guys able to follow? Can you guys get what I'm trying to say?
Clear, sir.
All right, so I really hope so. So again, if this is true, you will still answer this one. If this one is false, then you will still answer this one as your conclusion. All right, anyway, that's it for modus ponens. And then the next one is modus tollens. So we have here P conditional Q. So assuming that P is true and then Q is true. Okay. And then we have another hypothesis here wherein it's saying that this Q is actually false. Okay. So if that is the case, this one is actually in denial mode. Okay. So if we have this scenario in denial mode, we have to negate the hypothesis. So your result in here will be your hypothesis, but in a negated manner. Okay? So that is why from positive, it will become negative. So the same with this one, assuming that negated R is true, and then S is also true, and then we've proven that this S is actually false. So if we have this kind of setup, this one is in denial mode again, so we have to negate your hypothesis as your conclusion. Okay, so from negated R, it will become positive R, right? So that's it for modus tollens. Okay, so the only result that will make the conclusion as negated or positive is in a form of modus tollens. The rest, 1 to 5, so all of them are positive, depending on the construction. So did you guys get or get the modus tollens? Or just a little? Hello, are you guys still there?
Yes po, sir.
All right, that's good.
Yes, sir.
My only advice is just memorize this one. Okay, so if you can see this kind of format, then you have to negate your hypothesis. Same with this one. This kind of format, then you have to negate your hypothesis. Anyway, here are the other inference rules. We have here the conjunction, so you could read this one again as P and Q, and then this one as Q only, okay, since both of those are just true. And then in here, so this one is modus tollens. So we have a negated conclusion, so you have to negate your hypothesis as your result. And then we have here end elimination or simplification. So P and Q is concluded as P. So it could be this one or this one. So out of those two, they are both correct. So you can answer P or Q, right? Then we have here disjunction. And disjunction, how did this happen again? P or Q? Yeah, just remember. So in disjunction, so in here it is just saying that you could see that this P could be as a result as P or Q. Okay, because regardless of the value of your Q, P is always true. So you can have this kind of answer or in this manner. So the same with Q. So you can answer P or Q since Q is already true. Okay, and then as you all know in conjunction, I mean in disjunction, if there is already one true, then the entire statement is already true. right? And then here are the others. We have here hypothetical syllogism. So in here, I cannot give you guys a scenario, but if you're going to read this one, so your hypothesis here is P, okay? And then your conclusion is Q. But then again, this conclusion became hypothesis, and then we'll come up with another conclusion. So if you can see, or if you will see this kind of scenario on the future secrets, so you can just disregard this two in the middle, which is letter Q. Okay, so from conclusion to hypothesis. So you could say that this one is equal or equivalent to P conditional R. Okay, so this one is hypothetical. So instead of uh, you know jumping with another conclusion, so we've just come up with the first hypothesis and then come up with the final conclusion. So yeah, just memorize this one. Okay, so we call this one hypothetical syllogism. Then we have here disjunctive syllogism. So we have P or Q, and then P is already false, so we have to answer letter Q. And then another one is P or Q, and then we have proven, or we have here another hypothesis which is saying that Q is actually false, so we have to answer letter P. Okay, and then we have here contradiction, wherein again this one is already true, but this one is already proven false. So we don't have a choice but to answer. Sorry, this one is actually modus tollens. Okay, so if we have a false or a false conclusion, we have to negate the hypothesis. Right? So that is why we have here a positive P. Wherein we call this one contradiction. Alright, so that's it for the like a summary for inference rules for proposition. So do you guys have any clarification regarding with this one?
Answer.
Right. So since you have your copy with you, this inference rule summary, so I guess you'll be having a hard time in answering your secret since you don't need to memorize those tables or rules anymore. Right. So let's have an inference example. So it says here, use a truth table to prove the following. So we have here the inference format. So this one is actually also known as the modus ponens, if you guys can recall. So let S be the statement wherein from here you can construct this inference format into this. So again, how do we read this one? So P separated by this another hypothesis is actually an invisible N, which is now this one. Okay, and then we have P conditional Q, which is now this one. And then this bracket here is just the conclusion, okay, or the conditional. Okay. So this one now is equal with this expression. And then from here, we have to come up with a truth table, okay, which is now this one. All right. So we will not answer this one now one by one. So I'll just leave this one to you as your self-study or self-verification later on once we're done with our discussion. Okay. So yeah. So assuming that this is the result that we come up with this one. Okay. So we have here tautology. So we have now proven that this inference format or this expression is a true inference or for this one true expression, okay, with the use of inferencing rules. Okay. However, if we can or we have come up with true, false, true, true, okay, meaning this format or this expression is not legitimately done by the inferencing rule. Okay, maybe you uh, did another way of solving things, which is not included or which is not really part of the inference rule. Okay, so we call that one modus padus. So we will discuss that one later on. But for now, let's have another example or exercise rather. So prove that P conditional Q, not Q, is equal to not P. Okay, So from here, we can actually copy this entire hypothesis through here in our solution. And then as you can see right here, we didn't change anything, okay, aside from this one, right? So why did we convert this one into this one? Okay, because we are trying to prove that this hypothesis is equal to this conclusion. So using the laws of logic, so looking back on your laws of logic, we have contrapositive wherein P conditional Q is equal to negated Q conditional not P, which is a contrapositive. And then from here, we can now evaluate this one, okay, into negated P. So as you can see right here, we have here true negated Q and then conditional true not P. And then we have proved that this one is actually true. So from here, we could say that this one is equal to negated P. So how did we come up with that result? So just go back to modus ponens. So from here, this one is true, this one is still true. So that is why we have come up with this Q. So the same with this one. Whatever is the value of this one, so negated or not negated, then just copy that one as it is. All right, so that's how we prove such inferencing format using the laws of logic. Or actually, you can just go straight in here. So from here, this one is actually modus tollens, right? Do you guys agree? This one is modus tollens. Or no? So go back with your own copy. So yes, P and then Q is true, but in here we have proven that Q is actually false. Wherein this one is in a denial mode. And if we are in a denial mode, so we will answer or we will conclude the hypothesis, but in a negated format. So that is why we have here negated. So were you guys able to follow this one?
Yes, sir.
Yes, sir.
Really? Okay. So once we're done with our discussions, I would like you guys to practice. Okay. So you can find another examples on the internet. So try to, get some of those and then try to do that one on your own. So using your own approach. So in here, you can have two approach. So just by converting this one into a contrapositive and then come up with the negated P. Or you can just go straight just by applying the modus tollens, okay, which is now also equal to negated P, right? So yeah. Another one is this kind of inference format. So we have to prove that this hypothesis is actually equal with this conclusion P. So again, just copy the hypothesis as it is and put it into your solution. And then the next thing that we need to find is if you can eliminate other variables from another hypothesis. As you can see right here, we have this R and then R not Q. So we can actually combine those two into one. Okay. So in here, we've applied modus ponens. Okay. So we have proven that this one is actually true. So yeah, if it's modus ponens, that then just copy the conclusion as it is. So we have a result here of negated Q. And then from here, we have P or Q and then not Q. So again, this hypothesis is already proven true, but there is another hypothesis came out wherein it is saying that this Q is actually false. So from here, we have to get the true one or the true value, which is letter P. So that is why this expression is equal to this letter P. So did you guys get it?
Yes, sir.
All right.
Yes,
So
sir.
if you didn't get this one, then I suggest to go back on the inferencing rule. So maybe just memorize some of those or try to understand those, and then go back in here once you're done understanding how we've come up with such result or conclusion. Anyway, so next one here is number 2. Prove that this expression is equal to S. Right? So from here, we've arranged this one now in a manner that we can eliminate most of the variables. Wherein we've got this one first, P or Q, and then Q uh, conditional R. And then the next one is R conditional S, and then the last one is P. Okay, so this one first, P conditional Q, and then Q conditional R. So from here, this one fits perfectly for the hyposyllogism, okay, which is this one, wherein we can disregard the conclusion and then the hypothesis. All right, so just go straight from the first hypothesis and then the last conclusion, which is P conditional R. And then from here, you can just copy this one into this one. And then as you can see right here, again, this one fits perfectly for our hyposyllogism, wherein we can disregard this letter R and then just come up with P conditional S, right, which is not this one. And then from here, you can just copy this one and then put it here. And then you can apply here modus ponens. So this hypothesis is already proven too. So you can just simply copy the conclusion as it is as your final answer. Are you guys able to follow? So two
Sir.
hyposyllogism, and then the last one is modus ponens. So is there someone who's confused to this point? All right, so I'm assuming that none, okay, since no one is answering. Anyway, so let's have this last example. So prove that this expression is equal to negated P, right? So again, just put or just get all of those hypotheses and then put it in here, and then find hypothesis wherein you can eliminate 3 variables into 1 or 2 variables into 1. So in here, as you can see, we have true value for u and then true value for not x. And then somehow we have proven that this u is actually false. So we have to copy the true value, which is the negated x. Okay. And then from here, we can now combine this one into this one. So again, we have assumed that this x and then negated s is true, but then there is another hypothesis saying that this x is actually false. Okay, so all we need to do is just copy the true one, which is the negated s. And then from here, we can just combine this one into this negated s. Just put this r conditional s below. And then this r conditional s is already proven to be true. But then again, there is another hypothesis saying that this S is actually false. So modus tollens. So if we have this kind of denial mode, so just negate the hypothesis. So from positive R into negated R. And then this negated R can be deduced by combining this into P conditional R. So just put this one into here. And then assuming that this P conditional R is already proven to be true, but then again, we have another hypothesis saying that this R is actually false. So if we have a false conclusion, then this one is again modus tollens. Okay. So in modus tollens, we'll just copy the hypothesis and then negate its value. So from positive, it will become negative. So in here, we have now proven that these or those hypotheses is really equal with negated P. Okay. So here are the steps that we have or that we did. So first one is or elimination, and then the next one is or elimination, and then the last two is modus tollens. Okay. 1, 2, 3, 4. So first step, second step, third step, and then fourth step. Were you guys able to follow so far or no?
Medyo, sir.
Medyo, sir.
Medyo. Okay. So I'll give you guys a minute, okay, to analyze this one. Okay. So browse back using your own copy if you need. So here are the steps that we have applied. So again, if you have a question, don't be shy to ask.
Sir, question, sir.
Yes.
Do on making the solution, sir, do we need to start from bottom to top
Bottom to top.
to prove the
Actually, there is no proper arrangement on your hypothesis. Okay, so in here you can just simply put this P conditional R into the last one, R conditional S to the first one, is X or not S to the second one. So that's up to you on how you will arrange such expression. It's just that just find a hypothesis that you can think that you can reduce into a smaller variable. Like, for example, this one, P conditional R and then R conditional S. This one can actually be done using hypothetical syllogism. Okay, so you can actually come up with P conditional S. But take note, you're trying to prove that this one is equal to not P. Okay, so if your result is not equal to not P, then your ways of doing things or eliminating things is not correct. So you might want to try to change your approach. Okay. So maybe that is the
okay,
reason.
sir. Thank you, sir.
Okay. So how about the others? All right. So since we now only have 30 seconds, I guess, so we will just. Sorry for that one. I thought we still have 30 seconds, more or less. Anyway, so do you guys have a question so far? Or is there any other people who has a question? So another technique here is your goal should be only focusing on the conclusion. So just find a way to prove that these hypotheses are really equal with this conclusion. Okay, by applying, of course, the inference rule or the equivalence logic. Okay, so you can have a longer solution but come up with the same result, which is the conclusion, and you can actually come up with shorter solution but still come up with the same result. Then that's okay, as long as we have the same answer. It's just that we have different approach. So do you guys have a question before we proceed to the next one? Or do you guys need more time to analyze this one? And also, I guess the other tip or technique that you may apply here is practice. Okay, just need to familiarize yourself on how to solve such things. Okay, so you can find other examples on the internet and then try to, you know, compare your answers versus the answers of the internet. Because again, we can have different solutions but the same answer. All right, so since we can afford to stay here for 5 more minutes, so I'll just leave this one to you guys as your self-study or self-verification study. Okay, if you cannot really understood what happening here. Right? So it's practice, practice, and practice. So once you're done in doing your practice and then familiarizing everything, then you can now proceed and answer this secret. Okay? So this is another secret wherein you're going to write a proof of sequence for the assertion. So we have this inference format, and then we have the other expression wherein it's not in inference format. So in here, no problem. Just the same with our past examples. But for number 5 and 6, so you have to convert this one first into an inference format. And then from there, you can now proceed with the solutions like this. And then in answering this one, since yeah, I think it's doable in Microsoft Word, but it's super difficult, okay? Especially having this kind of bracket. I wasn't actually able to find this kind of bracket. We have the other way around, but yeah, that's a different bracket. So I will let you guys do this one using handwritten. Okay, solve this one using handwritten, but please write legibly and then take a picture of your solution and then your final answer clearly. Okay, so it should be clear, not pixelated. Okay, so there should be also a good lighting, a background light, so that I can see your solutions clearly. Okay. So yeah, that's it for your secret. Do you guys have any concern or clarification regarding with your secret?
None, sir.
How about the others? Any clarification or concern?
None, sir.
None, sir.
Wala po.
All right then. Okay. Okay, the next one is modus vadus, just like what I have said a while ago. Okay, so if you didn't follow the inference rule properly, you'll come up with a modus vadus result. So just like this one. Okay, so P conditional Q, and then we have proven that Q is actually true. This one is actually, no. In here, actually this one, the result should be Q. Okay, so we don't have rules wherein we're going to answer letter P. So the only way that we're going to answer letter P or the hypothesis is if this one is a modus tollens. And then for us to be able to say that this one is a modus tollens, if we have proven that the conclusion is actually false. But in here, they are both true. So as you can see, this one is incorrect as your conclusion. So if ever that you're going to verify this one using a truth table, this one is actually not a tautology. So if it's not a tautology, then this one is called already modus vadus, not a valid rule. Okay, so the same with this one. Okay, if ever you're going to come up with a truth table of this one. Okay, and then the same with this one. Having this kind of expression. So if you're going to analyze this one, so we have proven that P is actually false. However, if this one is true or false, we will still answer letter Q as it is. We will not change the truth value of this one, or we will not apply a negation. So that is why this one is also incorrect way of solving inferencing rule. So as you can see, if you're going to solve this one or construct a truth table from this one, you'll come up with this kind of result, and then there is one false on the truth table or the result. So this one is not a tautology also. So we call this one modus badus also. Right? So yeah, that's it for the modus badus. And then the next one is mathematical induction. So this one is a method of proving a formula wherein I think I wasn't able to put all of the definition. Anyway, so this is a method of proving a formula from long or from expanded formula into another formula, which is of course a fixed formula, wherein instead of writing a longer or expanded formula, if we can come up with deduce or a smaller or shorter formula, then we will just follow, of course, the smaller one. So in here, we will try to prove that one using mathematical induction. So we have here the principles or two basic principles. So step one is by replacing the formulas or the variables by one. And then we have to prove that they are true in terms of equivalence. So the left expression and then the right expression. After that, once you have proven that they are true after replacing the variable by one, then you can now proceed to step number two, which is called the inductive step. So if S1 is true for all I is less than n plus 1, then S n plus 1 should be also true. Okay. So in here, instead of just replacing the variable by 1, we will now go and replace the variable by n plus 1. So in here, we're just making the expression a little bit more difficult. And then it should be also true since we didn't change anything. It's just that we've just changed that variable by n plus 1. So for you to be able to appreciate this one, so what are those steps? What are you trying to say, sir? So we do have example here, okay? So we have to show that this expression, 1 plus 2 plus 3 plus up to the infinity, okay, is equal to this kind of expression or formula, okay? So again, instead of writing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus up to infinity, so if you can come up with one formula wherein this one is equal with this one, then why not, right? So we have here the solution. So we have to prove that this left expression is equal to your right expression, okay? So step number one. So just replace the variable by 1 or let n equal to 1. So just copy the letter n on the left side and then the entire expression on the right side. So just replace this one into 1 and then the n into 1 and into 1 and then simplify it. So as you can see right here, of course, simplify the parenthesis first. 1 plus 1 is equal to 2. And then 2 times 1 is 2. And then 2 divided by 2 is equal to 1. So in here, we have proven that this right expression is equal to your left expression if you replace the n by 1. Okay. However, if you really wanted to verify this one, whether this one is really correct, okay, or really equal with your left expression, you have to do this step number 2, wherein instead of just replacing, okay, the n by 1, you have to replace now this n by n plus 1. Okay. So again, we're not trying to change anything in here because whatever you're going to apply on the right side will be applied onto the left side. Okay. So from here, we have to show that, for example, just copy this one for now. Right side expression, n times n plus 1 divided by 2. Okay. And then replace them or replace the n by n plus 1. Okay. And then this is now the replace or the updated, okay, steps. And then just simplify this one and then you will come up with this kind of expression. N plus 1 times n plus 2 divided by 2. Okay. So now we have to show that this expression is equal on the left side expression. Okay. So how do we do that? So we're going to change the approach. So from here, just get this one, or we have to show that this one is equal to this one if we're going to add n plus 1 to the original expression that you have on the right side and then the original expression on the left side. Okay, so our goal here is to come up with the same expression. Okay, if we're going to add n plus 1 on the right side, which is this one is the original, and then n plus 1 on the left side also, which is this is also the original, right? So from here we could simplify this one into this. So how did we come up with this one? So again, in combining two expression, so just cross multiply this one. So 2 times n plus 1, and then the denominator of this one is 1. So 1 times n plus 1. And then whatever is the denominator of those two expressions, so just multiply it. So 2 times 1 is 2. So that's how we come up with this result. Okay. So were you guys able to follow up to this point?
Yes, sir.
Or quite confused?
Yes, sir.
Okay. So I bet that 80% you are quite confused if this is your first time. Okay. If ever that this is your first time learning about mathematical induction, okay, 80% you might be confused or lost right now. So you don't know what we are trying to do. Okay, so I highly suggest that once we're done with these basic examples, try to look on the other examples on the YouTube. Okay, so we have the same steps. Step 1, replace the n by 1. Step 2, replace the n by n plus 1, and we prove that form n plus 1 is really equal with your original expression if you're going to add n plus 1 on that one. Anyway, from here, there's actually so from here we are now saying that this one is equal to this expression, right? So maybe if you're going to analyze this one logically, okay, or with the use of your mind only, it's quite difficult. So that is why I'm going to show to you guys on how we've come up with such result. There you go. All right. And then let's change the size. So from here to here. So who were able to get this one? On how we've transformed this expression into this one. Is there anyone who's confused? Or it's okay?
It's okay, sir.
What is that? So
It's okay, sir.
I would say that it is not my problem anymore because you are already done with your algebra. So I'm really hoping that you guys already know how to, add certain variables, okay, into a single variable, or a single expression. So again, from here, we just cross multiply. So 2 times n plus 1, and then 1 times n plus 1, which is now equal to this one. Okay, then the next one, so we're trying to say that this one is also equal with this one. Okay, so how did we do that? So first is you have to expand this one. So n times n times 1. So just expand or distribute that one. So n squared plus n plus 2 times n, which is 2n, and then 2 times 1 is 2. Okay, divided by 2. So just simplify this one a little bit more. So n squared plus, so since we have the same variable here, so we can combine those two. So n plus 2n is equal to 3n plus 2. Okay, divided by 2. And then from here, if you're going to expand this n plus 1, n plus 2, this one is actually equal with this one. Okay, so let's see if they are really equal. N plus 1, all right, so I'll not show that one. So we'll just do the FOIL method. Okay. N times n is n squared. And then n times 2 is 2n, so plus 2n. And then 1 times n is n. And then 1 times 2 is 2. So simplify this one. So n squared plus 2n plus n is equal to 3n. And then plus 2 divided by 2. So that is why this expression is equal with this expression. So they are the same. Were you guys able to follow?
Yes, sir.
Yes, sir.
All right, that's good. So now we have now proven that this, this expression just by adding plus n plus 1 is really equal with this result that we have a while ago. All right, so that's mathematical induction, okay, proving that this right side expression is really equal with your left side expression if you will come up with a different approach like having this one n plus 1. Okay, then we have here another example. So show that if r is not equal to 1, then a plus a r raised to 1 plus a r raised to 2 plus and so on and so forth, wherein it's also incrementing by 1. So wherein we could say that this expression is actually equal with this one. Okay. So since we are dealing with call this one exponent, so we should start with 0. Okay. Why 0? Because if you're going to put there 1, then you're trying to neglect the first step already. So we have to start with 0 because any number that is raised to 0 is always equal to 1. Okay. So in here, just get the left side expression wherein this one, AR raised to n, and then just get the entire right expression. And then replace the n by 0. So the n became 0, n became 0, and then just simplify this one. Okay. So 0 plus 1 is 1, which is now this one. So a times r raised to 1 minus 1 divided by r minus 1. And then any number that is raised to 0 is 1. So that is why we have this 1 here. And then just simplify this one more. So a times 1 is a. And then in here, you can actually cancel this one out. So r raised to 1 is the same with this one. So we'll just cancel that one out, which is now equal to a. So from here, we have proven from step number 1 that this right side expression is really equal with your left side expression. Okay. So of course, we are not yet done. So we have to proceed on the step number 2. We're in making the n into n plus 1. Okay, so we have to show that just by replacing this 1 into n plus 1, we have to show that we can come up with the same result. So I didn't show the step-by-step solution anymore on how we come up with this one, but just by replacing the n into n plus 1, so this one will become n plus 1 plus 1. So from here, we can actually simplify that 1 into n plus 2, which is now this one. So you can actually do that one mentally. So that is why I didn't show the step-by-step solution anymore. Anyway, so how about if we're going to add n plus 1 or AR n plus 1 on the right side and then AR raised to n plus 1 on the left side. So we have to prove that this right side is still equal with this expression. So from here, again, just cross multiply this one. So r minus 1 times AR raised to n plus 1. And then 1, so we have here an invisible denominator, which is 1. So 1 times a times r raised to n plus 1 minus 1 is now this one. And then just multiply the denominators on both sides. So r minus 1 times 1 is r minus 1. So from here, this one now, if ever you're going to simplify this one a little bit more, this one is actually equal now with this one. So from here, we now have proven that this right side expression is really equal with the previous right side expression that we've got. Okay. So yeah, in mathematical induction, this one is actually a lot of practice. Will need you a lot of practice for you to be able to appreciate or master this one. Okay. But for now, were you guys able to follow this step-by-step solution and how we've come up with this final result?
Medyo.
Okay. So from here, just
Kinda.
try this one more. So on what part or on what topic of module 3 you've had a hard time in trying to understand? Is that the inferencing rule? Is it the proofing? Or the mathematical induction? None. So I'm hearing no one. So no one's responding. So meaning, lahat mahirap. All of the above are difficult. Am I correct?
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
So maybe mathematical induction is yes 100% difficult. So highly suggest you guys to explore more on the internet or other examples on how we've come up with a certain result. And then for the inference format, so this one is actually easy, but needs familiarization. Okay. And then what else? For negation, I guess no problem with this one. This one is super easy. And then identifying this one, whether this one is true or false. So very easy also. Okay. So let's practice more when it comes to mathematical induction and inferencing format or inferencing rule. Okay. So again, after you're done in understanding what is mathematical induction, so try to answer this seed rate. So don't worry, I only gave two seed rate. So prove that this expression is really equal with this expression just by doing the steps of mathematical induction. The same with this one. Okay. Right expression should be also equal with your left side expression. All right, so that's it for the module 1 part 3. So we are now actually done with the module 1. So we will now start our module 2 next meeting. So before we end this meeting for the day, do you guys have any other concern other than the mathematical induction?
None, sir.
How about the others? Any concern or clarification?
Wala naman po, sir.
None, sir.
Okay, so again, in answering this one, okay, so answer this one handwritten. Okay, so, but then again, you must write legibly so that I can understand your uh, handwritten. So I can check it properly. Because if I cannot understand it, then I just might mark it incorrect or wrong. Okay. So just write legibly and then take a picture of it clearly, okay, before uploading that one on our canvas. All right, so if you guys do not have a question anymore, so you guys may now go, and then good afternoon to all of you again.
Yes, sir.
Bye, sir.
Goodbye, and then thank you for coming.
Bye, sir.
Thank you, sir.
Goodbye.
Thank you, sir. Bye, sir.
Thank you, Doc.
Bye, sir.
Goodbye. How about you, Mr. Janeza and Mr. Rava? Do you guys have a question?
Wala na po, sir. Okay na.
Okay, so I'm ending this meeting now. So goodbye and then see you guys next meeting.